Okay, here we're going to talk about a couple of more properties that materials have. The first is Poisson's ratio. And in developing Poisson's ratio, we first need to recognize that when something elongates axially, it contracts laterally. What do I mean by that? Well, when it increases in length, say I've got tension on the thing, P acting on this, pull it out, it increases some length, delta, okay, to a new length, okay? When that happens, the actual cross-sectional area actually shrinks, or the radius shrinks by some delta prime, okay? Conversely, if I compress something, the middle actually increases. So if I shrink the length of it, the area actually increases, okay? So I have two separate strains that I'm looking at. The first is a longitudinal strain, which is what we're familiar with, the change in length over the original length, okay? And then we have a lateral strain, where it's basically the change in radius over the radius, which is what I have shown here in this picture. I've got a radius and then a delta prime. Okay. Now, the ratio of these strains is what Poisson's ratio is. Okay. So the ratio of the latitudinal strain over the longitudinal strain is Poisson's ratio. And there's a negative sign in front of that. Okay. And that's because, again, that idea that when one increases, the other decreases. So Poisson's ratio would be a positive value. Now, generally, these are between a quarter and a third. Okay, and this is a dimensionless number. Okay, but generally the Poisson's ratio is somewhere in that range. We'll talk more about the limits of it later on when we talk about generalized Hooke's law. But for now, just recognize that the Poisson's ratio is generally going to be in that 0.3 sort of range, plus or minus. Okay, and this is constant and depends on, it's different for every material. Okay, the other thing is we can also have a stress-strain curve in terms of shear. Okay, and it will have a very similar looking plot. Okay, where I plot the shear stress tau versus the shear strain gamma. Okay, and it'll follow that. Similarly, it'll have an elastic range, and then it'll have strain hardening, and then it'll wind up breaking. Okay, similar to tension, there in the elastic range is going to have a slope, and that slope is defined by G, where tau equals G times gamma, where the shear stress is that G times the shear strain, where G is either referred to as the shear modulus of elasticity or the modulus of rigidity. Okay, so either one of those is true. Again, this is very similar to Young's modulus of elasticity, just for shear as opposed to an axial load. Okay, and I can actually relate this to Young's modulus through Poisson's ratio, because again, that lateral strain and longitudinal strain are clearly related, as we talked about with Poisson's ratio. So I can relate through this equation, okay, that G and E are related through Poisson's ratio through this equation right here. Okay. Again, we're going to come back to this later on, just like talking about Poisson's ratio and some of the limits when we talk about generalized Hooke's law much later in like chapter 10. But for right now, just recognize that we also have a shear modulus and that it's related to Young's modulus by Poisson's ratio, which again is the ratio of latitudinal and longitudinal strain.